We start this class by looking into some problems with which has horizontal motion involved in it. So, the first problem is number 1, Canberra. The capital of Australia has a latitude of 35 degrees 17 minutes and 27 seconds. In Canberra, a horizontal cannon shot is fired such that it travels for 100 seconds. What will be the angular deviation and in which direction, right or left? Okay. So, for this particular problem, what is given is the latitude, which is 35 degrees 18 minutes and 27 seconds. First of all, what we need to do is we need to bring it to a decimal format, which will be 35 plus 18 by 60 plus 27 by 3600. Now, if you perform this, it will be something like 35 point, so 18 by 60. So, it will be, I will use my, I do not have a calculator, but I have a mobile which I can use as calculator. So, if I do that, it will be 35.3 for this particular term, and 27 divided by 3600 plus 0.3, yeah. So, it will be, so finally it will be 35.3075, right, and it is given as south, that is very important. Now, the angular deviation alpha is given as omega sin theta t. Omega is the angular velocity of Earth's rotation, sin theta is the latitude, which is given as 35.3075. So, all we need to do, and t is given as 100 seconds. So, we have to put these values in. So, it will be 7.3 into 10 to the power minus 5 into sine of this angle. So, once again I use my calculator here. So, it will be 0.578 into t is given as 100 seconds. So, the deviations, and if we calculate this, we will get this multiplied by 7.3, okay, into 100 equal to divided by, so it will be, yeah, 0.42 centimeters approximately, right. So, this is the angular, 0.42, it is a dimensionless number. So, 0.42 will be the angular deviation. So, alpha equal to 0.42 radians, this is the answer, right. So, this is question number 1a. Question number 1b is for the same place, that means at Canberra, which is given by 35.3075 3075 degrees south latitude. What will be the frequency of a plane of Foucault pendulum? Okay, so, let us come to the question here. What frequency does the plane of a Foucault pendulum will precede with? Will the motion be clockwise or counterclockwise? Okay, so, there is a second part of second part of this. So, we have to tell with whether the deviation will be towards the right or left. Now, it happened to be at the southern hemisphere, this S means southern hemisphere, and in southern hemisphere the deviation has to be left to the original direction. Okay. So, left is the right answer, right. Right. Now, let us move to the second part. What is the plane, what is the frequency of the plane, does the plane of a Foucault pendulum will precede with? So, we know that the frequency is given by omega equal to, or omega z, which is given by omega sin theta once again, right. So, again we are not looking for the time period, we are just looking for the frequency. So, we have to multiply 7.3 into 10 to the power minus 5, which is omega, that has to be multiplied with 0.5 0.578. Okay. So, this will give us some number, and now if I want to calculate the time period t, which will be given by 2 pi by omega sin theta. Now, recall that 2 pi by omega is 24, right. So, it will be or 2 pi by omega is 1 day essentially. So, it will be 1 day divided by sin theta, which will be 1 divided by 0.578, which will be, once again I use my calculator. Okay. So, 1 divided by 0.578 will be 1.7 day approximately. So, it will take almost more than 1.5 days for the plane of Foucault pendulum to make a complete rotation. So, if we start here, let us say to begin with, then the plane, again the plane will rotate, whether it will rotate clockwise or anti-clockwise. Now, please recall, in southern hemisphere, for a person standing on southern hemisphere, the earth seems to rotate clockwise, right. So, the plane of the pendulum will rotate anti-clockwise, right. So, it will make a complete precision in 1.7 days, right. Now, so with this we move to our next topic, which is motion under deviation due to Coriolis force under vertical motion. Let us consider we have a particle which is moving, which is falling from an height h of particle of mass m, which is not very important, we will see. Once again we level this as Ex, Ey and Ez. So, we want to see how much this particle will deviate from. So, ideally, in an ideal case, if it starts exactly on z axis, then it should fall at the origin. So, we want to see which direction and by what amount this particle will deviate due to the Coriolis force. Now, as the particle is falling straight, we can assume the velocity v, we can write it as minus z dot Ez cap. So, this is the form of the velocity. So, the Coriolis force F c will be 2m v cross omega, which is given by Ex cap, Ey cap, Ez cap, okay, 0 0 minus z cap. So, we have included this minus here, and we have 0 omega cos theta and omega sin theta, right. So, if we do that, we see finally only the Ex component will survive, because we have a 0 column here. So, if we calculate Ex, it will be this 0 minus of minus. So, there will be a plus omega cos theta z dot, right. So, if I write the force equations along 3 different axes, we get x double dot is equal to 2m, or m will cancel out because we are just writing the acceleration, omega cos theta, 2 omega cos theta z dot, y double dot is equal to 0 and z double dot is equal to minus g. Now, for the last relation, if we integrate it, we will get z dot is equal to minus gt and z is equal to h minus half g t square. And from here we can calculate the time of flight, which is the time which it will take to reach the ground. If we put z equal to 0, we get t max, which is 2h by g, right. Now, what we can do is we can substitute this with gt, and please remember we cannot write minus gt here because we have already included the minus sign here. So, what we need to do is we need to write x double dot is equal to 2 omega cos theta gt. Now integrating it once will give you omega cos theta g t square, this 2 will cancel, plus some constant c1. Now please recall that at t equal to 0, x equal to 0 and x dot is also equal to 0. So x equal to 0 means the initially it starts along above z axis only, above the origin on z axis only. So there is no x or y deviation. The second assumption essentially means that although, okay, so now think of this situation. We have already calculated the Coriolis force and we have seen that Coriolis force is acting along the east direction. Please remember that Ex is east, Ey is north and Ez is up, right. So the Coriolis force is acting along east direction. So there will be a deviation along east. Now this deviation along or force will cause a deviation along east, that means there will be a velocity component along east as well. Now this velocity component along east will insert another force on in the y direction. So there will be all these secondary effects, but because this force itself is too small, it is proportional to omega cos theta. Okay. So we are assuming that the secondary effects are vanishing, non-vanishing effect. So we are setting x dot equal to 0, y dot equal to 0 at any t. So this is a very important assumption we are making here, and this is a valid assumption. That means we are neglecting the second order effect. Neglecting second order effects. Okay. So this is a valid assumption given that the second order effects are actually very small. So we can use that x dot equal to 0, which immediately sets c1 equal to 0. Similarly, we can integrate it once more to get 1/3 omega cos theta g t cubed plus some c2, which we can also set equal to 0. So the maximum deviation is when we put t equal to tm, and we immediately see that this is nothing but omega cos theta. Now there will be a 2h cubed by g cubed, this will cancel out. Oh sorry, there is a root here, sorry. Okay. So if we include this and do the calculation, the final expression will be 8h cubed by g. Yeah, so there will be a g outside and there will be a g to the power 3 by 2 inside, minus 3 by 2. So it will give you a g to the power half, right. So this is the maximum deviation, and the maximum deviation is due east. Okay. So this is the maximum deviation and this is due east, right, because x axis, if you recall, is the eastern direction. Okay. So this is the important result, because we start from the top and we see that in the deviation is given due east. And also please note that the expression, what is the final expression we got, is omega cos theta. I mean it's proportional to omega cos theta. So does not matter if we stay in the northern hemisphere or southern hemisphere, it will give you a deviation which is due east, right. So with this we also briefly introduce the effect of centrifugal acceleration, that is the last topic of this chapter. Okay, so this is our earth. Any point on earth which is at the radius of earth is r0, at any point the centrifugal acceleration, which is given by omega cross r, at any point r equal to r0, you can carefully consider the components of omega, and r is a radial vector. So the direction of r at this particular point is this. So if you do this careful calculation, I mean if carefully check the sign of this vector, then it can be shown that this vector is just at any point it is along this particular direction. So, basically if I join that point with the axis of rotation, this will be the extended direction of this particular vector. Now, what is the effect? Recall that the force due to gravity, which will cause g, the acceleration due to gravity, is along this line. So, basically g vector acts along this line. Now, this force is there, that is also a force which is omnipresent, and the magnitude of this term will be omega square sin square theta, theta being the latitude. So, I am leaving it up to you to prove this, that omega cross r will have a magnitude of this and direction of this. Okay. So, this I can so sorry, it will be omega square r cos theta. I am sorry. So, it will be omega square r 0 cos theta, not that, right. So, if this is the case, then this is a force which is present at any point. Of course, the magnitude will change depending on the value of theta, right. So, if it will be, if it is cos theta dependence, then it will be 0 at the poles and maximum at the equator, right. Now, at equator does not have much of a problem, because this one acts along this line, this one the g acts along that line. So, they kind of cancels each other. So, at any point they are not in the equal direction, I mean equal or opposite, sorry, they are not in the opposite direction. So, the effective g at any point, if this is my direction of g vector, this is my direction of this particular centrifugal acceleration, which we will call f c. So, my effective g is a vector sum of these two, right. So, this is my g effective, which is a vector sum of g plus f c, right. So, this is not, so the g effective as we see is not along the line joining that particular point to the center of the earth, but which is a line which is slightly deviated from it. Of course, this deviation will be small, because it has a omega square term, this f c has a omega square term, but it is not 0, there is a considerable amount of deviation, and this particular line is called the plumb line. Okay. So, anyway, this is what I wanted to express briefly. So, all I can tell you that you can calculate in principle the change in magnitude of g at any point on earth using this relation, right. Now, with this we move to the second problem of this problem set. A particle of mass m is thrown vertically upwards from origin with initial velocity v 0. Determine the deviation from origin when it hits the ground. Now, it is a slight deviation of the problem which we have already performed. Instead of starting from a height h, it is starting from the origin, let us say. So, we have E x cap, E y cap and E z cap. Okay. So, the particle of interest starts from this with the initial velocity v 0 in the vertical direction, and then reaches a maximum height, and then it comes back here, right. So, once again we have to write the equation of motion. Here please understand that v is given by v 0 minus g t, right. Okay. So, I will not write a vector equation, that will be a bit confusing. The magnitude of v is at any point is given by v 0 minus g t, right. So, as the velocity is in the upward direction, what we can do is we can once again calculate the Coriolis forces, and it can be shown, I am leaving it to you to do the exact calculation. This will be 2 omega cos theta z dot, right. y double dot as usual is equal to 0 and z double dot is equal to minus g. Now, we see that because the motion is in the upward direction, there is a negative sign. So, the force is not towards east, but towards west, right. This is up. Now, if we again substitute z dot, which will be given by V 0 minus g t at any point, taking this initial consideration into account. So, we get x double dot is equal to 2 omega cos theta V 0 minus g t, right. So, after once again we have to integrate it twice, and the final value will be, I am just writing the final expression, will be minus 2 omega cos theta V 0 t square by 2 minus 1/6 g t cubed, right. So, this will be the final expression. Now, z, if I integrate, we will get V 0 t minus half square, right. Now, from here what we can get is once again a total time of flight by setting z equal to 0. It is a quadratic, so it will have two roots, one for t equal to 0, we will have z equal to 0, and once for 2 V 0 by g, just directly from this relation set z equal to 0, and you will get T m is equal to 2 V 0 by g. So, when we put this into this relation to get a total maximum deviation, what we get is minus 4/3 omega cos theta V 0 cubed by g square, right. So, this is the final answer, and because of the minus sign, this deviation is due west. Now, this is a very interesting observation, because if you recall in the previous problem what we did, the deviation was due east, and now the deviation is due west. Now, in the previous problem we started from this point and the particle hit the ground, not here, but somewhere along x axis, right. But in this case, when we start from here, the particle comes back and hits the ground somewhere in the y, somewhere along minus x axis. Why it is so, I am just leaving on to you. Now, before we finish, what we can do is we can quickly look up into this problem once more, look at this particular expression for x m, which was the case when the particle was dropped from a certain height. So, by the way, if you find out the maximum height h and reduce this expression in terms of that, it will be exactly, you will find that it will be exactly 4 times this expression there with a minus sign here. So, let us examine this expression, then we will get a feel for this expression also. Very quickly, x m is equal to 1/3 omega cos theta 8 h cubed by g to the power half. So, if we put say x is equal to 100 meter, h is equal to 100 meters, what are the values of this deviation we get? So, for theta equal to 45 degrees, does not matter if it is north or south, because it is a cos theta dependence, we will get x m is approximately 1.54 centimeters, and for the same height theta equal to 90 degree, okay, theta equal to 90 degree means we will get, theta equal to 0 degree, where we will get maximum deviation, we will get x is equal to x m is equal to 2.2 centimeters. So, you see that the deviations are small when we are compared to a height of 100 meters, the deviation is small. But now consider the case when the object will be deviated from a height of few kilometers, then these numbers are not small. So, these are significant numbers. Now, as I said, when we are throwing the object, this particular case, when we are throwing the object from this one, from this point and it comes back, this it is not only due west, but it will be exactly the same expression multiplied by 4. So, in this particular case x m will be minus 4 by third omega cos theta 8 h cubed by g to the power half. We have to substitute, we have to find and we have to replace V 0 by h. So, in that case if we use the same number x m will be, so this will be towards east. So, it will be almost 6 centimeters towards west, and in this case it will be x m approximately 8.8 approximately 9 centimeter towards west. So, you see these numbers are not very insignificant anymore. So, if we can throw a stone at the height up to a height of 100 meters, when it comes back it deviates by 6 centimeters at 45-degree latitude, and at 0-degree latitude the deviation is almost 9 centimeter. So, these numbers are not very insignificant. With this we end this class. So, we will see you in the next class. Thank you.